Okay, hi Year 11. This video is going to have a look at what combinations are and how they differ from permutations. So it's kind of a warm-up to exercise 14E in our Extension Maths course. So what we've been doing for the past few lessons is having a look at what we can do with permutations. Well, this topic from 14E and 14F, we're going to have a little bit of a look at combinations. So when we had a look at permutations, it was a method of arranging all the members of a group in a particular order, and order was important with a permutation. When we have a look at a combination, the combination is a selection of elements from a collection, but the order that we are looking at those things at is not important. So that's the first way to distinguish between a permutation. It has order, and we need to know the different orders or arrangements, and a combination doesn't. And there's a nice example below to help us tell the difference. Okay, and remember, with permutations, we care about the order of the elements, whereas with a combination, we don't. And sometimes the language we use in our everyday talking, we actually use combinations and permutations incorrectly. And here's an example. It says, for example, say your locker combo, and that's in inverted commas for a reason, is 5432. If you enter 4325 in your locker, it won't open because it's a different order, basically a permutation. So the permutations of 2345 are all of these numbers below down here. So when you say you have a locker combination, you actually don't have a locker combination. You have a locker permutation of which you have one of these values of 4 digits that are listed below. Your locker combo or your locker combination would be different. It's a specific permutation of 2, 3, 4, and 5. So if your locker worked truly by combination, you should be able to enter any of those digits above and have it open for you. So let's say it again. So 2, 3, 4, and 5 below are listed all the different permutations of that number, but a combination of 2, 3, 4, and 5, we don't care about the order. We just care that somewhere in that group of 4 numbers there's a 2, and there's a 3, and there's a 4, and there's a 5. And that's what's really important for us to remember. One has an order that's important and one doesn't. I'm going to use this example here to get us a little bit more understanding of combinations and permutations and how we can come up with a combinations formula from the permutations formula. So I can just give these to you, but I would prefer for you to have a look at where they come from. So the question I've got listed below is how many 5-card hands can be made from a standard pack of 52 playing cards. So they're the cards with the jacks, the kings, the queens, the hearts, diamonds, clubs, and spades. So there's normally 52 cards in there, and we want to look at how many hands can be made. So what we've been doing with these sorts of questions is we've been popping boxes in there. So I'm just going to pop lines today. Okay, so I'm first of all going to think of these as a permutation and pretend that order is important, or that we really want to look at the order. So the first place of our 5 hand of cards has 52 choices that we can take. And our second position is only going to have 51 because one of those 52 has been chosen. So remember doing these previously? Our third hand in our card, our third card in our hand would have 50 different ways we can choose because we've already used 2 of those cards up and there's only 50 to choose from. And so on, 49 and 48. So using our rules of multiplication in combinatorics, we would then multiply all of those numbers together. And we would end up with 311,875,200 different permutations. So this was our number of permutations. Now, remembering back to our formula for that, we could have found this using our permutation formula or button, on our calculator, and that would become from 52p5. We were choosing 5 different things from 52 in total, where we were looking at all of the different I keep using combinations, all of the different orders that were within that. And the other thing that we used for this was, it was written as, we'll just go a generic formula, NPR was written as n factorial on n minus r factorial. So another way that we could have worked this one out was 52 factorial on 52 minus 5 factorial, which is 52 factorial on 47 factorial. So you could work that out on your calculator in any of those ways. But with this question, we want to have a look at, I want to look at how many 5-card hands. So I don't know if you have played cards before, but when we're playing cards, you normally hold them in your hand and you can shuffle the cards into any order that you want. There's no necessity to have them in a particular order. So in this case, for this question, I actually want to have a look at the solution with a combination instead of a permutation. So with my 5 cards, I don't care what order they are in. So what I want to do is get rid of the necessity for the order of my cards. So I'm going to divide my permutations above, up here, my 311 million, by the number of ways that I could have those 5 cards in my hand. And that will get rid of the order that I don't need when there's a combination. So my first card could take 5 different ways, my second 4 different ways, my third 3, and so on. And we're really good at these ones now. And that's the same as 5 factorial, which is 120. So the number of unique 5-card hands where I don't need to look at the order of the hands can be found by dividing my 311,875,200 by the 120, which was the number of ways that they could be arranged within that 5-card hand. I'm popping that in the calculator. I'm going to end up with, which is 2,598,960, which is still a really, really big number, but this is the number of combinations. I've taken out the necessity for order, and I've got the number of combinations of cards in my 5-card hand where I can hold those 5 cards in any order I like. So what I want to have a look at now is really how did we come up with these values here? I'm going to pop our formulas in that we just did and pop them in there for me. So my 311,875,200 I found by 52 times 51 times 50 times 49 times 48. And I divided that by 120, which I found by going 5 factorial. Now, I don't know if you can see a pattern there, but we started at 52 and we moved down to 48. So we've got a whole heap of numbers that are below 48 missing if I was to think of the top line as 52 factorial. So that's what I want to do. I want to make my top line 52 factorial. I've still got my 5 factorial on the bottom, but my 52 factorial didn't go down to 1, did it? It stopped at 48. So that must mean that from 47 onwards, so my 47 factorial down to 1, so 47 times 46 times 45, has been cancelled out with a 47 factorial on the bottom. So what I can do is I can pop a 47 factorial there. So what's actually happening, let's pop it over here. If I had my 52 factorial on the top line, just show you in case you don't get this, let's have a look. So now my top line looks like that. I've still got my 5 factorial there, and I popped a 47 factorial on the bottom line, which looks like this. So what has basically happened is I've got my 52 factorial on the top there, and what has cancelled out is this part here has cancelled out with this part here. And so what I'm actually left with is what I had originally up on this side up here. So if I cancel those out, I now still have my 5 factorial on the bottom that I had over here. So this 5 factorial is still over here. My 52 down to 48 is still down here. So I could write that as 52 factorial over 5 factorial times 47 factorial. Now the reason I've done that, because I've wanted to get a formula that I can use that is related to the permutations formula, and I will show you soon how that is. But let's have a look at how else we could write this. I could write my 52 factorial on the top line, my 5 factorial, and I can get my 47 factorial from 52 minus 5 factorial, which looks very, very similar to the permutations formula that we had. So I'm going to write this in a generic form. I'm going to write this formula as n factorial, because that was the number of cards we had, and I wanted to choose 5 cards from that 52. So I'm going to pop that as my r factorial, or some people use k instead. And I'm going to pop under there as well as my n minus r factorial. And this is my formula that I'm going to be using for my combination. So this is my combination formula. And how I can actually write that is n choose k. The c is written as a choose. It's also sometimes seen as n k like that. It's also our n factorial on n minus r factorial, r factorial. What I might do is, we're mostly using r, so I'm going to change those k's to r's for us there. Now there's a button that we can use for n choose r in our calculator. I've got the abacus here, so I'll pop that up there. It sits above the divided by button there. That's our NCR, or our combinations button. So if we look at what we did up above, we had 52 over 5 factorial, 52 minus 5 factorial. That would be 52, and I'm choosing 5 from that 52. And that was our not our 3 million, that was our 2,598,960. So I'm going to go and see if I can get that on my calculator by doing 52 choose 5. So let's do that on here. So I've got 52. I'm going to choose 5 from that 52, and there's my number there, 2,598,960, which is the same as what we got up here. So yep, the formula works for our combination. I could also have just popped in my calculator 52 over 5 factorial, 52 minus 5 factorial. So they're all telling me the same thing. So you might be able to see there, but I would like to show you, and I think this one's really important, and a lot of people miss out on this, is how our formulas are related. So our NCR is equal to our NPR with r factorial on the bottom. So our NPR was n factorial over n minus r factorial. So there we are. So n factorial over n minus r factorial is our NPR, and if we divide that by r factorial, we will get our arrangements, or the order taken out of our question. So with the question above, we had 52 cards, of which we were to pick 5. There's our permutation that we got, and that was our very large number, and we'll look at that in a second. And we are going to take out the order of 5 factorial, and then we will have a combination. And that's the same as saying 52, C, or choose 5. So let's have a look at that on our calculator so that we can see that the numbers do match. Okay, so if I had 52 and I was going to make a permutation out of that and pick 5 cards, I would have my 311 million. And that is order being important, where if I picked a heart first, that made a difference if I picked that last. But because we're playing our card game, we don't need order. So I'm going to divide that by 5 factorial. That removes the order and makes it a combination, and I end up with my 2 million different combinations.